Welcome back. Our next subject, energy and changes of state. And you remember state is not California and Nevada, it is solid, liquid, and gas. And so what we're going to talk about in actually a fairly quantitative manner, quantitative means numerically, we're going to get some numbers here, is how much energy does it take to melt something? How much energy does it take to boil something? How much energy does it take when you freeze something? How much energy does it take when you deposit something, or when you condense something, going from a gas to a liquid? But our first question we're just going to think about is this. Does freezing something take energy or give off energy? So just pause for a moment and think about your answer to that question. Does it take energy to freeze, or does it give off energy to freeze? All right. Most people think about it, and the first thing they come up with is this: if I want to freeze water, I have to plug in a freezer. I have to plug that thing into the wall. I have to give it energy in order to freeze it, because it doesn't freeze on its own. So they say, hey, well, it takes energy to freeze. And that's a perfectly valid initial response to thinking about it. But let's think about it on a molecular scale. So freezing is going from a liquid to a solid. And in the liquid, what do we know? That we've got these little molecules that are moving around each other, right? They're constantly moving. There's some molecular motion. In a solid, all of a sudden, they essentially stop moving, and they're all fixed in one place. So if I go from having a lot of motion to having no motion, right? There's some energy here, right? And we went essentially from energy to lower or no energy. So if we went from energy to lower energy, where did that energy go? Well, it turns out it gets given off. And it gets given off as heat. So it turns out that when we freeze something, we are giving off energy. And it's totally not our experience. We totally don't have the experience of freezing something giving off energy because we have to put it in the freezer. But that's what happens on a molecular scale. The reason we have to put it in the freezer is because it's not cold in our room. We have to make it cold enough to freeze. We actually have to take the energy out of the air in the freezer so that the water in the freezer can give its energy to the air in the freezer. And that's what we're doing when we freeze it. So we are giving off heat. And the reason I can write this equation the way I did is because energy is conserved in the world, in the universe even, is that if we have energy over here and we have energy over here, they better be equal unless energy is given off or taken. The analogy to that is money, right? We can't print money because we're not governments. So if I have 20 bucks, that's it. I have 20 bucks, no matter what I do with it. If I have 15 and then I give away 5 to a friend, right? If I have $20 now and in 5 minutes I have $10, it's not just that $10 disappeared into the universe. That $10 went somewhere. I gave it away. On the other hand, if I have $20 now and I have $30 in the future, that means that somewhere I gained money. And when we write these equations here, what we do is if we give it away, we write it on the right-hand side. We say, hey, it's a product. We're making it. And we're going to look more into chemical reactions and writing products and reactants later in the class. But that's what we do. We write it over on the right-hand side as giving away. I had lots of energy here. I had less energy here, which means I gave it away. I had lots of money here. I had less money here, which means I gave some of my money away. So let's look at the whole temperature cycle. And I love this picture. It's one of my favorite pictures in the old version of the textbook, which they've since removed. Okay. Is our little snowman friend. And our little snowman friend shows all the different phases of water: solid, liquid, and gas. We've got the solid here in the snowman, a liquid in a melted snowman, and a gas in the cloud snowman. And there's words here talking about the different phase changes that happen. A phase change is changing from one state to another, from a solid to a liquid, from a liquid to a gas. And we're familiar with most of these terms. When you go from a solid to a liquid, we call that melting. When you go from a liquid to a solid, we call that freezing. A little less familiar to most people is the technical terms from going from a from a liquid to a gas is called vaporization, and going from a gas to a liquid is called condensation. And you've probably heard condensation referred to, water condensation, things like that, water condensing on something. And that is the right term. So if you have a cold glass of lemonade, water is going to condense on the outside, and it's gaseous water from the air turning into liquid water on your cup. The funny ones over here are these two. It's going from a solid directly to a gas without ever forming a liquid, and going from a gas directly to a solid without ever forming a liquid. And most people at first have trouble with that. They're like, no, that can't happen. But you have some experience of that if you've ever looked at dry ice. A block of dry ice just goes straight from a solid to a gas without ever making a puddle of CO2. Dry ice is made of CO2. So it goes directly from a solid to a gas in a process called sublimation. And if we reversed that process, you'd get the process of deposition, going directly from a gas to a solid. And one other place you might have ever experienced that is if you've ever had a pack of frozen vegetables in your freezer, and it had been there for a year or two, maybe still sealed in the package. You've never opened the package. You've got a plastic package. Water can't get in. Water can't get out. The thing is frozen. But what happens is if you open up those peas after 2 years, you have these little shriveled peas and you have a chunk of ice. Where did that ice come from, and how did peas shrivel? Well, it turns out they're subliming. The water in the peas is going directly from a solid to a gas, and it's filling up the bag. And then since it's cold, it then deposits directly from a gas to a solid in a chunk of ice. And you get this process of essentially freeze drying your peas on a slow basis. So those are the technical terms for all of our different phase changes. But they also have energy associated with them. We decided that it gives off energy to freeze something, which can be a little bit conceptually difficult. But if we think about the other way, does it take energy or give off energy to melt something? And we think about, solid not moving, liquid moving. In order to go from not moving to moving, I got to give something energy, right? A ball sitting there on a desk, if I want it to move, I got to give it energy. And so we can think about melting something must require energy. So it takes energy to melt. But the universe likes to do things in a way that's reproducible. So if it takes energy to melt, I must have the opposite happen when I do the opposite. And this releases energy. So going from motion to no motion, that energy's got to go somewhere, and it gets released off into the world. Now, how much energy? I'm going to give you some numbers here for water. You don't need to memorize them at all, but it'll give us some numbers to work with. And if you're talking about the energy it takes to melt, it is 80 calories per gram. So to melt 1 gram of water takes 80 calories of energy. So if we release that energy, what do you think we get? We get exactly the opposite. And so that's going to be also 80 calories per gram. Now you'll see some books and some people use positive numbers for both of these, and that's understandable, but I'm going to think about it a different way. If I've got a checkbook and I write a check to someone, what do I put that in as? A positive or a negative? I put that in as a negative, so when I lose money, when money goes out of my account, I count that as a negative. When money comes in, when they deposit money into my account, I count that as a positive. So anytime we've got losing energy, I'm going to put a negative in front of there. And that's just a convention we use in chemistry. When you lose it, we call it negative. When you gain it, we call it positive, very similar to a bank account. So I'm going to put that negative in there. How about vaporization and condensation? Again, I'm going to give you those numbers, but let's think about them for a moment. Do you expect that number to be bigger or smaller? So remember, going from a solid, not really moving, to a liquid, there's some motion. And then we go from some motion in a liquid to how much motion was there in a gas? It was like 500 miles an hour. It's crazy motion. So if you're going from some motion to crazy motion, that's going to take a lot of energy, right? And so this number hopefully is going to be much larger, and it is. The energy of vaporization, what we call the heat of vaporization, is 540 calories per gram for water. For other substances, it's different, but it's also large compared to the energy it takes to melt. So the heat of vaporization, that's just a term we use. The heat of is 540 calories per gram. What do you think it is for condensation? Hopefully you're like, hey, well, it's got to be the same, but opposite. So minus 540 calories per gram. Excuse me, and that would be called the heat of condensation. How about sublimation? Sublimation. Well, it turns out sublimation is similar to a process of melting and vaporization, so you just add the two. 540 plus 80 is 620 calories per gram, and deposition minus 620 calories per gram. Again, we don't need to know or memorize any of these numbers, but we do need to be familiar with the terminology. When we say the heat of vaporization is 540, the heat of condensation is minus 540, the heat of freezing is negative 80. Unfortunately, for melting, we don't call it the heat of melting. Hey, I didn't make this stuff up, sorry. We don't call it the heat of melting, we call it the heat of fusion. So the heat of fusion, that's a U. For water is 80 calories per gram. For other substances, it would be a different number. So when we're talking about melting, it's heat of fusion. For everybody else, it's just its name. Heat of vaporization, heat of condensation, heat of sublimation, heat of deposition. So let's go ahead and do something with these numbers. Let's try to calculate how much energy it takes to boil 450 grams of water. How much energy? And when we look at our units, right, we've got units of calories per gram. Well, 1 gram of water is going to be, let's look back up here, 540, right? Because boiling is the same thing as vaporization. Boil is going from a liquid to a gas. Vaporization is going from liquid to a gas. So you need to know those two terminologies are related to one another. So we know that for 1 gram, it's 540. For 2 grams, it would be double that. For 450, it would be 450 times that. But there is a kind of general equation we use that the energy is equal to the mass, the mass times the heat of the phase change. And I use just a capital H there because that's what's often used. Specifically here, we're going to say that the energy is the mass times the heat of vaporization. And people will use VAP for short there. Since I'm boiling, that's the process of vaporization. So I said energy is mass times heat of vaporization. If I was melting, I'd say energy is mass times the heat of fusion. If I was subliming, I'd say energy is mass times the heat of sublimation. And so we can plug directly into this guy, 450 grams times 540 calories per gram. You multiply that out, you're going to get 2.4 times 10 to the 5th calories. A fairly large number. It takes a lot of energy to boil water. 2.4 times 10 to the 5th calories. We had 2 sig figs here, 2 sig figs here, and so we kept 2 sig figs in our answer. So here we go. The heat of fusion of methanol is 102 joules per gram. How much heat is needed to melt 7.35 grams of methanol? So you see the numbers different here because it's a different substance, but the process is exactly the same. Pause the video, try it out, come back and see what you get. All right. Hopefully you wrote down that energy is mass times the heat of fusion. And so you say energy is 7.35 grams times 102 joules per gram. And you'll notice our units are different here. Here we had joules, the other one we had calories. Remember, they're interchangeable just by the 4.184 factor. And so it's perfectly fine to use one or the other. If I ask for one or the other, you may have to do a conversion. If I asked for this in calories, you'd calculate it in joules. and then convert it to calories. So here we go, 7.35 times 102 is going to be down there at 750 joules. That dot there is just to make sure I have 3 significant figures in my answer, because I had 3 sig figs here and 3 sig figs in my other number. So there we go. 750 joules is how much energy it takes to melt 7.35 grams of methanol. That's our discussion of heats of phase changes. Thanks.